Hello everyone. In this video I am going to explain the stable multivibrator. Okay, so stable multivibrator using 555 timer. So as you basically know, this an stable multivibrator, which is often called as your free running multivibrator, is a rectangular wave generator. Unlike the monostable multivibrator, where we need to have a trigger input in pin number 2, here in case of a stable multivibrator, we don't need to any external input, so it's a kind of oscillator. It's not kind of, it's an oscillator. It's a free running oscillator, or we can say rectangular wave generator. Okay. So it does not require any external trigger pulse, and hence the name is free running. Okay, free running multivibrator. However, the time duration or time during which the output is either high or low is being determined by the resistor and the capacitor connected externally and the timer, along with the timer. So let's start this. Here, as you can see, the circuit. This is your stable multivibrator circuit, where this is your pin number 8, the VCC, then a reset pin number 4, then this is your discharge pin, then threshold 6 and 7 the trigger, and this is your control pin, and this is your ground, and this is your output. Pin number 3 is the output. So the externally this RA and RB is connected like this way, and the capacitor C. So these three are responsible, RA, RB and C are responsible for defining the time, on time and off time, that is your pulse, on time and off time of the pulse, output pulse. So and this C1, this capacitor is fixed at 0.01 microfarad, and the VCC can be 5 to 10 volt. Okay, sorry, 5 to 15 volt. Here I have given say 10 volt. And this is the internal part or internal circuitry of the 555 timer. So under this box, it is the internal part. This two op-amps behaving here as a comparator, this RS flip-flop, and this is just an output amplifier. And this Q1 and the Q2 are, Q2 is your PNP transistor and Q1 is PNP transistor. And here internally 3 5K 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 ohm resistors are connected so as to maintain 2/3 of the VCC here and 1/3 of the VCC here at the input. So here in the inverting terminal 2/3 of the VCC, and here in this comparator in inverting terminal is connected with that 1/3 of the VCC. Okay, and depending on this trigger input and this threshold input, this comparator output either will be 0 or 1. Now as you can see, suppose initially the output is high. Okay, when the output is high, this capacitor C, here it is this. So this capacitor C gets charged up to the VCC through RA and the R. However, as soon as the voltage across the capacitor equals to 2/3 of the VCC, when this voltage goes up till 2/3 of the VCC, then the comparator 1, this comparator 1 triggers the flip-flops. So it will be triggers this R input of the flip-flop, and the output. So since R becomes 1, because this capacitor get 2/3 of the VCC and it is also 2/3 of the VCC already. Since the capacitor charges 2/3 of the VCC, here it will be 2/3 of the VCC. It is already at the 2/3 of the VCC. Output will be output will be, yes, output will be 0 here, and here it will be 1, and hence this is the Q bar output. So Q bar output will be 0 here. So when it is output is 0, this output will go to low. Now the this capacitor, once this output goes low, this transistor is switch on. Now the capacitor C, this C start discharging through RB and the transistor Q1. So it will go through this way. since it is on, so it will go through this way. This capacitor will discharge through this path to the ground through RB and the capacitor Q1. Okay, when the voltage across the capacitor equals, so when it is discharging, up till how much it discharges? It discharges up till 1/3 of the VCC. So when the capacitor voltage goes up to appears to be 1/3 of the VCC, then the comparator 2 output. So this comparator 2 outputs get triggered. Okay, so this comparator 2 output, that means as input get triggers, the flip flop of the output then goes high, because it is it will be 0, it will be 1, and so it is 0, and this will be high. Then this cycle repeats again. Okay, so the output of the voltage, output voltage and the capacitor voltage can be shown here. Yeah, so this is the output voltage and this is the voltage across the capacitor C. Now see, during the on time, I mean when the capacitor is surging, this capacitor surges up to the VCC through RB and RA. So this is your surging. So up till 2/3 of the VCC it gets surged. Suppose this is your 2/3 of the VCC. So this surging time, during this surging time, the output will high. Okay, so this surging time, this output will be high, and once it is high, the moment it goes low, this transistor switches on and capacitor start discharging. So this capacitor is discharging, and it will discharge up till 1/3 of the VCC, and during that time when the capacitor is discharging through RB and this Q1, this output will go low. So the output will go low here, and once it reaches this capacitor while discharged up till 1/3 of the VCC, so once capacitor voltage reaches the 1/3 of the VCC, then the cycle repeats again. So it is so and so forth, it is going on. So this is a free running output waveform. That is why it is called free running multivibrator, and it's a rectangular waveform. Okay, I mean a square waveform, square wave output. Okay, now if you go through the derivation, you will find that this surging time and discharging time totally depends on this RA, RB and C. So I am not deriving here, but if you go through the derivation of this surging time Tc, it will come out to be 0.69 into RA plus RB into C, and the discharging time Td will be your 0.69 RB into C. So therefore this Tc is the on time for this pulse, and Td, that is discharging time, is the off time for this pulse. So total time of the output pulse, I mean output waveform, is in one period the total time is T1 plus T off. Okay, that is nothing but Tc plus Td. So T is equal to Tc plus Td, which will come out to be 0.69 into Ra plus twice Rb whole to C. Okay, now the frequency is 1 by T, so 1 by 0.69 Ra plus twice Rb into C. Now 1 by 0.69 is nothing but 1.45 into Ra plus twice Rb into C. Okay, here as you can see in this frequency there is no term involved the VCC. So that means in this free running frequency oscillator or the multivibrator, this frequency of oscillation does not depend on the bias voltage VCC. Now when it is a square wave, since it is a square wave, output square wave, so the important parameter here is the duty cycle. As you know, this duty cycle defines whether on time off time is equal, or on time is greater than off time, or off time is greater than on time. So if on time and off time are both are equal, that means it's a 50% duty cycle, then your on time is greater than off time, that means it is more than 50%. If on time is less than the off time, then it is less than the 50% duty cycle. Okay, so this duty cycle is primarily defined simply by the on time, or here it is surging time, divided by the total time into 100%. Okay, this is the standard definition of a duty cycle: on time divided by the total time into 100%. Okay, so your total time is suppose 100 and this is 50, so then it will be 50%. That is your 50% duty cycle where square of that is on time and off time are equal. Now if it is less than 50 on time divided by this, so it will be less than the 50%. Likewise, so from this TC already we know this is 0.69 into RA into RB into C, and the total T is this. So if we put it like this, so it will come out to be RA plus RB divided by RA plus twice RB into 100. So this is your duty cycle. Okay, so these are the prerequisite things while experimenting with this timer as an stable multivibrator. So these are your prerequisite things for experimenting the stable multivibrator. So now let's move to the multisim. So in the new project, so in this new project, here first we'll see the multivibrator, the timer. Okay, so this timer can be here in all families. Just type 555. Sorry, this should be all groups. So in the 555 timer rated, so this I have chosen here. Then I need your register, the basics. You will get register. This is your register. So one register, then one more register. Values will change later on. Then what else? So we need two capacitors. So this is a capacitor. Values will change later on. This is one, and one more capacitor. Then from the source, power source, VCC is required. So VCC, then ground is required, and that's it. Okay, so these are the things required. So now let us connect. So first, this is the level of your timer. Okay, VCC here will VCC is connected here, and pin number 8, and this pin number 4, this reset pin also connected to the VCC. Then your this register, let me flip it. Okay, so it will be in between here. This reset and this source. Okay, this threshold and trigger get common. Okay, then this register again, let me flip it. This will be connected here. Along with this, then a capacitor. So this is I'm rotating again. So this capacitor is connected here. Then there is a ground connected here. Okay, so this capacitor get grounded, and another capacitor. So this capacitor is connected here along with. So this capacitor gets grounded here, and okay, so that's all the circuit. automatically issue. Okay. Now from here I'll use one function generator is not required. This is oscillator, so only an oscilloscope. So here I am connecting the oscilloscope. Okay, so the channel A of the oscilloscope is connected with the output, and channel B is connected with your capacitor output. Then the ground is connected here. Okay, now change the level. Suppose this is I'm making it as your level as RA, then this I'm changing it as RB, then I'm making it as C only, this I'm making it as C1. Okay, now the values for the VCC I am making 10 volt. Then this R1 cell, let for the first time I'll make it as 2.2K. Then suppose this one I'll make it as 3.9K. Okay, and this I am making as 0.1 microfarad, and this has to be 0.01 microfarad. So 0.01 microfarad. That's all. Then save it here. Okay, it's done. So run it. Now click on this. This arrow. Oh, just a minute. Something is wrong. Yes, yes, sorry. This voltage should not be. This is 105 given. It should be 10 volt. It's too high. Okay. So run it again. Yes. For the better representation, let me expand it little. This arrow. Okay. Now what I'll do is first let me put both in the ground. Channel A is in ground already, channel is already ground, so let us put AC. Yes, this is the output, then AC, this is the capacitor. So you see, during the surging time the on pulse is generated, and during the surging up till 1/3 of the VCC, this your off time of the pulse is being generated. Okay, now let us evaluate this, the timing. Okay, and see whether it that theoretically and practically whether it is equal or not. Okay, so let's see that. Okay, so for that I'll just pause it. Yes. then I'll use this scale. Okay, so this scale is T1 and this scale is T2. Okay, now if you look at this T1 scale, the voltage is showing here, actually this point. Okay, that means it is -6, so upward it will be less than yeah. So if I put it here, yes, it is 3.9 volt. Okay, now the time, this time T1 is 151.316 and T2 is at okay. So time difference between these two is the time difference between these two is your T2 minus T1 is your 414.013 microsecond. Okay, one is your 151 320 milliseconds. So because it is showing here the microsecond, okay, if you look at it in a millisecond, it would be okay, then also it is okay. Let me put it, yes, microsecond, no problem. So yes, so this is your on time. This on time is your 421.975 microseconds. So let me put it here. Same way you can check in another also, you will get the same. Okay, yes, this one. So 425 slightly greater than, let it be 425 microsecond, 425.955, 425.955. let's see here how much it is showing. 421.9, slightly here and there. Okay, so I'll consider it as say 425 microsecond. 425 microsecond, yes. So that is your T on. So let me write it here as T on or TC. Okay, so let me write it here as TC is equal to how much it was, 425 point, okay, let it be 425 times 425 into 10 to the power minus 6 microseconds, so 10 to the power minus 6, okay, second. And similarly now let us see the discharging time or the off time. Okay, off time is how much, see here, so this is your off time. So off time you see 274.682, so let it be 274 microsecond. Okay, 270 278, yes, 278 microsecond. Okay, so let it be 278 microsecond. So this is your practical. So let me write it as practical. Okay, practical. Okay. Now total time. So this total time practical. So this total time practical, it will be here this one plus this one. So this is 425 plus 278. So this is equal to your 703 microsecond. Okay, so 703 microsecond. So this is your practically the total time duration. So frequency will be your 1 by t. So frequency is a practical, let me put it as practical. Okay, which will be equal to 1 upon t. So t practical. So which is equal to 1 divided by 703 into 10 to the power minus this. Okay, so which will be equal to your 1.422 kilohertz. Okay, now let's see the same thing in theoretically. Okay, so this is the theoretical value. Okay, so theoretical which will be equal to this. So 0.69 into your array. So how much I have given the array? Array is 2.2 kilohertz. Sorry, 2.2 kilo ohm. So 2.2 into 10 to the power 2.2 into 10 to the power 3, 10 to the power 3, then plus RB is your RB is 3.9. So 3.9 and C is your 1.1 microfarad. So into 0.1 microfarad. So 10 to the power minus 6. Okay, 10 to the power minus 6. So which will be equal to your 0.4209 millisecond. Okay, so which is equal to your 420.9 microsecond. Okay, 420.9 microsecond. Okay. So here the TC practical was 425 microsecond, and here it is 420.9 microsecond. Similarly, TD practical, theoretical, TD theoretical is your this TD 0.69 RBC. So which is your 0.69 RB, yes, 0.69 RBC. So 0.69 into RB is your 3.9 into 10 to the power 3, that is 3.9 kilo ohm. Okay, and into C is 0.1 microfarad, so it will come out to be, it will come out to be here 0.2691 millisecond. That means 269.1. Oh, sorry, here I made the sense. So 269.1 microsecond. Okay, so the TD practical was 278 microsecond. Here we got 269 microseconds, slightly here and there. Now the total T, so total T will be here, so T theoretical, sorry, which is equal to 0.69 into RA plus RB plus C. So which will be equal to 0.69 into this one, but here there is a 2, okay, twice RB. So this is equal to your 690 microsecond. Okay, 690 microsecond. The same you can get by simply adding up these two. So it is 910, then 960, then so on. Yes, if we add up these and these, it will be 690 microsecond. Okay, so this is total time. Then the frequency. So your frequency is theoretically the frequency is equal to your 1.45 divided by RA plus twice RB into C. So 1.45 RA, so it is equal to RA. So what is RA? RA is 2.2K. This is your RA. then RB is 3.9, sorry, 3.9, so here there is a 2 multiplied here, okay, and C is your 0.1 microsecond. Okay, so which will be equal to it will be 1.45 kilohertz. Okay, so this is your F. Now see, this is practically it is 1.422 kilohertz is the frequency. Here theoretically, let me put it as theoretical. Okay, so theoretically 145 kilohertz. So there is a slight difference, hardly 0.3 difference, 0.3 kilohertz, 0.3 kilohertz difference. Okay, that is 30 hertz. Then you see it is practical on time, TC on time 425 microsecond, and theoretically on time 420, so 5 microsecond there is a difference, and off time, discharging time, that is off time 278 microsecond, practically, theoretically it is 269, so hardly here 78 237 microsecond, sorry, how much, 269 and 278, so 9 microsecond difference. Total time it is 703, and here it is 69T, so 13 microsecond time difference, and frequency 1.422 kilohertz, and it is 1.45, that is around 30 hertz difference. Okay, and if you would like to calculate exactly the surging and this 2/3 of VCC, whether it is or not, so you can check it by this is the maximum voltage at which it is surge, so therefore it is your channel B, so it is this T1, yes, 1 points, just a minute. Okay, so as it is in AC, so it will be in 1.69. now to get the actual voltage you should put it as DC, the CRO. So you see the CRO, this both are, this T1 T2 both are in same position, so it is your 6.638 volt. So I have given the VCC as 10 volt, so 2/3 of the 10, 20, so 6.67, so it is coming out 6.63. Similarly, if you look at voltage here, it will be 1/3 of the VCC, this is 2, so 3.3, 1/3 of the VCC is around 3.3 volt, so it is showing here 3.35, or so little more it will go, yes, 3.380 volt. Okay, that means it is discharging up till 1/3 of the VCC and surging up till 2/3 of the VCC, so it's correct. Okay, so that's all. So what you need to do is, likewise here I have shown you one experiment with one set of experiment, that is for a 2.2 kilohertz, RB 3.9 kilohertz, C 0.1 microfarad. So sorry, RA 2.2 kilo ohm, RB 3.9 kilo ohm, C 0.1 microfarad. So what you do is you change this and make a set of around 5. Okay. Now this same stable multivibrator can be used as a square wave. But right now, as you see here, this waveform is not perfectly square wave. That means on time, off time is different. As we have this duty cycle I have not calculated, right? Okay, so percentage of the duty cycle, so you have to calculate that also. So it is Tc by Tn. If we make it theoretical, it will be this only. So it is equal to here it is this 2 is not there, then this into 100, so it will be equal to 61% your duty cycle, which is your theoretical, right? Theoretical, but practically I'll calculate this practically. So it is Tc practical, right? So your Tc practical this is your Tc practical. So this is your Tc practical by T practical, and which is equal to, so what is your Tc practical? Your Tc practical, this one 425.425 microsecond. So this is your 425 microsecond divided by your T practical, total T practical, this is your T practical 703 microsecond. So it is 703 microsecond, which will be equal to into 100%, which is equal to 60.45. Sorry, 60.45%. So there is a slight difference of these two. So it is 61% theoretically and practically 60.45% of duty cycle. Okay. So this is your roughly 61% duty cycle. Now to make it 50%, if I make it 50% duty cycle, so then it becomes exactly a square wave. So that means the same circuit can be used exactly a square wave circuit by making this duty cycle 50%. Now if we look at the formula of the duty cycle here, to make it 50%, RB must be RA must be 0. If it is RA is 0, then only RB cancels, so it is 50%. So that means in this circuit you have to make this RA 0. So what will happen when RA is 0? So when RA is 0, so that means this capacitor that discharge through, actually it charged directly to RB, and while it is discharged through this one RB and Q1, then what will happen? An extra current will flow. Okay, high current will flow, extra current is supplied to this Q1 transistor, and slowly this Q1 transistor will get damaged because of the high current flowing through. And once this Q1 transistor get damaged, so as a result this timer will get damaged soon. Okay, so that is why we simply cannot put this, we simply cannot put this array 0 to make this as a perfect square wave oscillator. So rather what we can do is I can minimize it to make it perfect square wave. So I'll show you another one here. It's already been designed. So you see I have already tuned it and I make it 300 ohm instead of 2.2k here as I used earlier 2.2k. Then instead of that I make use of 300. So now if I run it, you can see almost a perfect square wave, almost perfect square wave. You can see the time here. So if on time and off time are equal, then it is perfect square wave. So on time, as you see, 291 microsecond. Now let's check off time. It is 303, slightly greater. So it is not exactly perfectly square wave, but near to the square wave. So I can tune this resistor further below this 3 array. It is 291 and this is 303. Okay, so perfectly, not perfectly square wave, but slightly, I mean approximately a square wave, 100% square wave. Okay, so further if we decrease it, then it can go towards the perfection, but it starts malfunctioning because, as I mentioned, because of this low resistance, a heavy current will flow through during the discharge. Heavy current will flow through this Q1 and Q1 get damaged soon, and as a result this timer will get damaged. So what we can do is along with a very low resistance of say 100 ohm, if we connect a 10 kilo ohm pot here, potentiometer, and a diode for safety purpose, a diode P type upside, N type downside. So if I connect a diode here at this point and with a very high resistance, very low resistance along with a potentiometer, by tuning the potentiometer, then I can tune up at the perfect square wave. Also at that point we have to connect one decoupling capacitor here, that is from VCC to ground. Okay, VCC to ground, around 10 microfarad of decoupling capacitor, then we can make it of almost perfect square wave. Okay, so you please try that one. Okay, so that's all. So here in this video we have learned about the stable multivibrator, how this stable multivibrator works. I explained this with this internal circuitry of the timer along with the externally connected RA, RB and C. Okay, so this waveforms we obtained already, and calculations, the surging time, that is on time, discharging time of the capacitor, that is off time, total time is this. Okay, and accordingly frequency 1 by time, and duty cycle is the on time by total time into 100%. Okay, and practically and theoretically we obtain slight difference which is negligible. Okay, now for considering for RA is equal to 2.2 kilo ohm and RB is equal to 3.9 kilo ohm. Okay, then later we have seen how to make the same circuit as a perfect square wave. So for perfect square wave, theoretically RA should be 0, but if practically I put RA 0, that will slowly damage the IC, timer IC. So it is not advised to put RA directly short. Better we put a potentiometer across it, and along with that across the RP we put a diode, so as to make it towards the perfect square wave. Okay, so you carry out this experiment with different sets of RA, RB and C, and for any further query contact me. Thank you very much.